Humans read text, but computers process data structures in memory. Turning something that is human readable into data structures is the job of a parser. Parsers take HTML and turn them into the document object model that is used to lay out a web page. They take the source code of a computer program and turn it into pages of error messages due to a misplaced semicolon. I'm going to explain how a parser works by showing you how to write one, but I'm going to go a step further than that. I am going to introduce to you the core skills programmers use when they are tackling new problems. Basically, I'm going to show you how a programmer thinks about programming. The type of parser I'm going to explain is called a recursive descent parser or a top-down parser. It is the simplest type of general use parser, so it is something that is pretty easy to explain. It also has some downsides. That means that it's not used in high-performance applications, but it is a good starting point. A parser takes in raw human-readable text and generates from that a parse tree. This structured tree can then be further processed by a computer program into whatever format is most useful for the role. Let's make up a simple language for our example. Our language will consist of numbers, the plus sign, the multiplication sign, and brackets. We will follow the binding rules from those irritating Facebook posts. Okay, irritating Facebook post doesn't narrow it down too much, but I'm pretty sure you know the one I'm talking about. We are going to have brackets bind the strongest, then multiplication and addition. So a statement like this will get parsed into this parse tree. Also, we are just going to ignore any white space in our language. The first step is to define formally the grammar of the language. We are going to do this by creating grammar rule. Each grammar rule says what a part of the language is made up of, progressively subdividing the language down until we get to the unsplittable atoms of the language. Let's call the topmost rule of our language an expression. We could call it anything, and quite frankly, some of the most difficult parts of programming is thinking up good names for things because we have so much freedom there. Now, our job is to work out what an expression consists of. It becomes a little bit like a puzzle solving game. Since plus binds the weakest and will always be on top of the parse tree, then we know the expression must feature the plus rule. So our expression must have within it the structure of expression consists of something plus something. But we also know not all expressions have plus signs. So we can extend this to or something. We know we can have chains of pluses without any limits. The way we can make unlimited chains of pluses is to make this rule recursive. For technical reasons, it is handy if the recursion is not on the left. So our expression will need to look something like this. Expression is something plus expression or something else. Now we can fill in the remaining blanks with the next layer down in our grammar. Expression is term plus expression or term. We will define what term is next. At this time, you should start to be coming to terms with defining a grammar. This is one of the prime skills of solving programming problems. Divide and conquer. Programming is a complex task, and it quickly becomes impossible to hold it all in your head. So we split a big task into smaller, doable tasks. So next is the term grammar rule. Since times binds the next tightest after addition, we know that times has to be on this level. Term is something times something. We can apply the same logic about repetitions and options we had for addition to work out the term should look something like this. Term is operand times term, or it is operand. We haven't even started programming yet, but here's the next key insight for programming. If you see that something common, just reuse the solution you used before. At the lowest level, we have the operand. Since brackets find the tightest, we know that they must be down here. And since numbers can't syntactically be split up, we know that they have to exist at this level as well. So we can say operand equals open bracket, expression, close bracket, or number. Now, the names expression, term, and operand are totally arbitrary. These names are there to act as reminders for us. What is more important is the relationship between the rules. Now, I want to be super accessible to everyone. So rather than using a specific programming language, I'm going to be giving examples using pseudocode. Pseudocode is not really a programming language, but more a way of sketching out logic that a real programming language would need without going into the specifics of any language. The first thing we should think about is what is going into and out of our parser. The function parse takes a string, which we put in the text variable, and returns maybe a parse tree. A string is the type computers use to represent human readable text. The metaphor is that they are characters connected together on a common string. This function returns maybe a parse tree because it's always possible for parsing to fail if it is fed something that is not parsable. I go more into maybe types in this video, but the short explanation is that a maybe type can either be the base type or a special value called nothing. Now, let's talk about how we are going to implement this parsing. In a computer system, parsing is implemented by two separate but equally important subprocesses. The lexical analyzer that tokenizes the string and the syntactic analyzer which structures the tokens. The job of the lexical analyzer is to take the raw string and create tokens from it. Since numbers are atomic in this grammar, it collects together the digits into entire numbers, and it also removes any white space. I'm not going to explain the lexical analyzer in this video, but rather I'm going to treat it like it has already been implemented. Function lex takes a variable of type string and returns maybe an array of token. Function parse takes a variable text of type string and maybe returns a parse tree. Assign to the variable maybe token the value returned from calling lex on the variable text. We can detect errors at the lexing stage. So, case maybe tokens. In the case of nothing, return nothing. Nothing comes of nothing. The case statement basically checks the value that is in the variable and does the thing with the matching case. Calling a return statement ends the function immediately and returns as the value of the function whatever the argument to the return statement is. If there isn't an error, then we can assign the token to a variable to be used later. Some of you who are more used to programming might think of what I'm doing is a little bit verbose. However, I'm writing this to make it extra clear. Then, the next step in processing is to do the syntax analysis. Unlike the lexical analysis that operates on a character-by-character basis, syntax works on the entire document. That means the syntactical analyzer is more complex than the streamlined lexer. This is another common thing programmers use. Have a pre-processing stage that simplifies the data to make processing easier. It's another way to divide jobs into simpler subparts. We know what needs to go in and out of this parse expression function. The function parse expression takes an array of token into the variable tokens and maybe returns a parse tree. However, thinking about it, in this grammar, it is possible to have expressions that start at places that are not at the beginning of the string and end at not the end. So to facilitate that, let's adjust our function slightly. Function parse expression takes an array of token into the variable tokens and an integer value into the variable offset. It maybe returns a pair containing parseTree and integer. With this stub written, and a stub is basically a hollowed out function which we use for work in progress, we can finish off our parse function. Assign to maybe tree the value that's returned by parse expression when called on the variable tokens with the offset value of 0. In the case of maybe tree, if the value is nothing, then return nothing. If it is a just value, then just return that tree. Now, that is looking good. So let us fill in our code for parse expression. The first thing it should do is check if it has a sum. Again, we're going to put off working out how to do that exactly until later. Assign to the variable maybe sum whatever is returned from parse sum on tokens at the offset. In the case that maybe sum is just sum with a new offset, then return just the expression created from the sum parse with the new offset. If parse sum fails, then it might just be a term. So we should parse it as a term next. Assign to maybe term, parse term with the tokens at the offset. In the case of maybe term, if it is just term with a new offset, return just expression from a term with that new offset. So we now have parsing an expression defined. We can go on to parsing a sum. Again, we define what is coming in and out of the function. It has the same type as parse expression. Parse sum takes an array of token into the variable tokens and an integer into the variable offset. And it maybe returns a pair of parseTree and integer. This time, rather than dealing with choices between alternatives, we are dealing with a sequence. We will start with a parser for the term. If this fails, we know the rest isn't going to work, so we can return nothing in this case. Maybe term is assigned the return value of parse term when called with tokens and offset. In the case of maybe term, if it is the just case, set term tree and term offset to the first and second returned value from parse term. If nothing is in maybe term, then return nothing. After we've parsed the term, the offset will be set after that term, where the plus should be. So we can add another parser for plus. Maybe plus, set to parse plus, tokens, term offset, case, maybe plus, etc., etc. Then we can end off following with the trailing expression. Maybe expression, same pattern. Now, we can create a new tree from the subtrees. Again, I'm not going into how this function is going to work. The biggest part of programming is managing cognitive load. Nobody is smart enough to hold anything but the most simple computer program in their head all at once. So it makes sense to divide a task into smaller parts so that you can only have to understand one part at a time. Assign to sum tree, make sum tree from term tree, plus tree, and expression tree. Return just sum tree and the final expression offset. Solving the definition of parse plus is pretty simple. You can just check that the token at the offset is plus and then return the offset incremented by 1. For all the other parse literals, like plus, times, and the numbers, and open bracket and close bracket, I'm just going to assume that they have the same type of code here. Let's go and define parse term. The first thing you're going to realize that it's going to be basically the same code for parse expression with a few words changed. We could just cut and paste the definition and then change all the names.
Did you just copy-paste that from somewhere?
That's programming.
It would look something like this. This, in fact, is something that's often done with a lot of production code. Frequently, we use cut and paste to reuse code. It is not the best practice, but it is something that happens in real world because we don't have much time. However, we can also make use of a much more powerful tool. We can abstract out the common elements in these two functions, we are going to create what is called a higher level function, a function that takes in and returns functions. To make this more convenient, let's first define a type for our parser functions. The type parser is defined as a function that takes an array of token and an integer and maybe returns a pair of parseTree and integer. Also, we're going to have a function type for the thing that creates the new parseTree from the code below. We'll call it treeLifter. Type treeLifter is defined as a function that takes a parseTree and returns a parseTree. With these two types defined, we can now go on and define our new function. As always, we set up its types to give us an understanding of what it's going to be doing. The function parseAlt takes an array of pairs of parser and treeLifter and puts them into a variable called parsers. It will then return a parser. To support the functions we've currently defined in this program, we would only need something that supports two alternatives. However, making something that supports an arbitrary number of alternatives is almost as easy and will allow us to extend this program to more complex grammars. Sometimes one of the dangers in programming is overgeneralizing, creating a complex solution that handles more cases than you need. However, in this simple situation, I don't think it's going to be a problem. Since we know that this has to return a parser function, let's do that as the first step. If we declare a function without a name, it becomes an anonymous function. Return a function that takes an array of token into a variable called tokens and an integer into a variable called offset, and maybe returns a pair of a parseTree and an integer. Next, we are going to use a for loop to step over each element in our parser array. For each element in parsers, assign that pair to the variables p and tl. We can use the code we used before, but adapted for our generic case. Maybe element, assign to the variable maybe element the value returned by calling the function p on tokens and offset. In the case that maybe element is the just case, return just the pair of element processed through TL and the element offset. If we get through all of the loop, that means we must have tried all the alternatives. So we return nothing to indicate that this attempt didn't work. Return nothing. With this new function, we can rewrite the parser functions we had. In this pseudocode, assigning an anonymous function to a name makes it into a named function. Assign to parseExpression the return value of parseAlt, taking an array of parseSum, expression from sum, and parseTerm, expression from term. Assign to parseTerm the return value of parseAlt, parseProduct, term from product, parseOperand, term from operand. This taking out repeated code and replacing it with more compact code is called refactoring and is a very common task. Though sometimes in a professional setting, you can take refactoring too far and create code that is unreadably abstract and dense. Knowing when to stop refactoring and when to start is a judgment call that you tend to learn from with experience. Now, we know that parseProduct is going to be just like parseSum. Let us create a higher level function for doing a sequence of parser. First, we'll create a handy helper type. The type treeJoiner is a function that takes an array of parseTree and returns a parseTree. Now we can define our sequence function. Function parseSequence, array of parser into parsers, treeJoiner into joiner, returns a parser. Again, we know it's going to return an anonymous function, so we can just jot that down. This time, we are going to have to add another for loop going over the elements in the parser array, processing them one after the other. In most languages, we would have to declare an array to put the subtrees in, but since this is pseudocode, we are just going to act like the language knows what we intend to do. For each value between 0 and the last index of the array parsers, put that into I. Then assign to maybe element the value returned by calling the ith element in the parsers array with the values tokens and offset. In the case that maybe term is a just value, assign the ith element of subtrees, the returned parsing tree, and update offset to the new offset value returned from the parser. If the case was nothing, then immediately return nothing. Then, if we make it through the loop, we combine all the subtrees. Return just a pair containing the value returned from calling tree joiner on the subtrees and offset. Now, we can refactor this all and adjust the other functions to support it. Parsum is defined as parse sequence of the array containing parse term, parse plus, parse expression, and a make sum tree, while parse product is defined by the return value of parse sequence for parse operand, parse times, and parse term with make prod tree. And now we can make a parser for the operand. Parse operand is defined by parse alt with parse number and make operand from number, or parse brackets, make operand from brackets. And we can finish it off with a parser for the brackets case. Parse brackets is defined as parse sequence for parse open bracket, parse expression, parse close bracket, make brackets. I was going to do a step-by-step animation of how this algorithm parses, but honestly, it didn't turn out that good. So instead, I'm going to put a link in the description if you would like to see it. The top-down parser spends a lot of its time trying alternatives and having to roll back to try other alternatives. But since I keep calling this a top-down parser, you might guess that there's an alternative bottom-up parser. If this video generates enough interest, I'll do a follow-up video on bottom-up parsers and perhaps Lexes as well. Thank you very much for watching this video. And if you want to see more of my content, please consider subscribing and sharing it to your friends who are interested in topics like this. Thank you very much.